Short number 6, observed matter-antimatter asymmetry. Attention, I strongly suggest you should watch the 5 previous shorts before watching this one. In the previous shorts, we focused our attention on the common waves studied in non-relativistic quantum mechanics. Until now, everything said about particles is also valid for antiparticles. In this short we will talk about the exotic waves where particles and antiparticles have total energy equal to EB, mc2. In addition, we will talk a little bit more about antiparticles. Now we are ready to go. Observed matter-antimatter asymmetry. We are formed and surrounded by matter formed by atoms and molecules. However, there are almost no antiatoms nor antimolecules in the observable universe. According to current physical theories, this should not happen because we should also be surrounded by antimatter. Why are we not surrounded by antimatter? It is worth pointing out again the following. Our current physical theories predict we should be surrounded by antimatter, but we are not surrounded by antimatter. In what follows, a possible explanation for this mystery will be presented. There is no wave associated with a classical particle, but there are 2 waves associated with a relativistic quantum particle. Strictly, all quantum particles are relativistic quantum particles. This means there always are 2 waves associated with a relativistic quantum particle. If a quantum particle gets naked, the particle loses both waves and behaves like a classical particle. In previous shorts, we have focused our attention on the common wave where the particle has energy equal to EA plus mc2. Until now, everything said about particles is also valid for antiparticles. However, we will proceed in what follows to break the theoretical matter-antimatter symmetry. This can be done by proposing that a charged quantum particle electrostatically interacts with itself, but in a different way that the corresponding charged antiparticle interacts with itself. First, let us talk about antiparticles. Let's assume that the electrostatic self-interaction of a charged antiparticle with itself always produces a positive potential energy. This means that the potential energy of an isolated charged antiparticle is always positive, independently of the wave where the antiparticle is in. The potential energy increases if the spatial confinement of the antiparticle increases. Discounted the energy associated with the mass, the total energy of an isolated antiparticle is the sum of its kinetic and potential energies. If the antiparticle is in the common wave with energy EA plus mc2, its kinetic energy is positive, therefore, there is not a local minimum for the total antiparticle energy. This means the common wave associated with the antiparticle cannot be spatially localized by its repulsive electrostatic self-interaction. In contrast, it is easy to show that, if the antiparticle is in the exotic wave with total energy equal to EB, mc2, then the kinetic energy of a spatially confined free antiparticle is negative. Moreover, the absolute value of the kinetic energy increases if the spatial confinement of the free antiparticle increases. The opposite behavior of the kinetic and potential energies determines the possible existence and the size of the antiparticle's exotic wave where its total energy is maximum. This would be the size of the exotic wave where the antiparticle has a total energy equal to EB, mc2. By solving the PPGP equation corresponding to the exotic wave, we can calculate the values of the negative kinetic energy of an antiparticle in a one-dimensional infinite well. Using these results, we obtained an extremely interesting outcome. If the absolute value of the charge of the antiparticle is smaller than the Planck charge, then the exotic wave associated to the antiparticle has a non-null size. The Planck charge is approximately 11 times the absolute value of the electron charge, E. This means that if the absolute value of the charge of a quantum antiparticle is smaller than 11 e, then there is an exotic wave associated to the quantum antiparticle. The quantum antiparticle is then a quantum antiparticle. However, if the absolute value of the charge of a quantum antiparticle is larger than the Planck charge, the exotic wave associated to the antiparticle collapses to a point. The quantum antiparticle gets naked, the antiparticle loses both waves and behaves like a classical antiparticle. This explains the mystery. We are not surrounded by antimatter living beings formed by complex molecules of antimatter because antimatter atoms are not stable. Many atoms formed by matter are stable. Quantum mechanics was developed for explaining the observed stability of atoms made of matter. Only charged quantum clouds can form stable atoms. In this statement, the word quantum is fundamental, and it implies there are two waves associated with a charged cloud. However, a cloud of positrons with a charge larger than 11 e is not a quantum object but a classical object. Therefore, antiatoms with an atomic number larger than 11 cannot be stable. These antiatoms have never been observed. All these mean the absence of classical antimatter objects around us constitutes an overwhelming amount of evidence about the validity of Einstein's special theory of relativity. This everyday evidence also supports our hypothesis about the electrostatic interaction of an antiparticle with itself. Please, stop and think about it. Please, think carefully about it. Okay, we found a plausible explanation about the notable absence of antimatter around us. But why we are surrounded by matter? We must break the theoretical matter-antimatter symmetry in current physics theories for explaining the abundance of matter around us. This can be done by accepting that a charged particle electrostatically interacts with itself in a different way that a charged antiparticle interacts with itself. For instance, the potential energy resulting from the electrostatic repulsion of a particle by itself could be positive if the particle is in a common wave with total energy equal to E8 plus mc2. However, the potential energy resulting from the electrostatic repulsion of a particle by itself should be negative if the particle is in an exotic wave with total energy equal to EB, mc2. This guarantees the exotic wave associated with the particle never collapses to a point due to the electrostatic self-interaction. Details about this topic can be found in a recently published book titled Relativistic and Non-Relativistic Quantum Mechanics, both at once. This book was published in September 2023 by Springer Nature, in the undergraduate lecture notes and physics book series. The book was written by Professor Luis Grave de Peralta and his collaborators from the Department of Physics and Astronomy at Texas Tech University, Lubbock, Texas, USA. This book is based on the use of the Poveda-Poya-Grave de Peralta, PPGP, equations. In addition, the authors use the PPGP equations for illuminating discussions about the following topics. The frontiers between the classical and quantum worlds. How the interplay between quantum mechanics and relativity determines the existence of black holes. The observed asymmetry between matter and antimatter. A Spanish translation of this book is also available in BookBaby.